Hello, and welcome to Math 40S, Probability and Odds, Unit 3. So this will be the third unit in this math series. Please go ahead and put your name at the top so I know who it is. Okay, probability and odds I think is one of the more difficult units for myself. Other people find that it's okay, but we'll see. So, probability, we have some notes. Tina takes groups on camping trips in British Columbia. She is planning a trip this weekend. She read that the probability of rain is 30% on Friday, 10% on Saturday, and 80% on Sunday. On which day is it most likely to rain? And on which day is it least likely to rain? It is most likely to rain on Sunday. It is least likely to rain on Saturday. And that's just from the numbers. B, what other situations where you have seen probability used to tell the likelihood of an event happening? The likelihood of rolling a 5 on a die, the likelihood that a red car is drawn from a deck, the likelihood that I will win a prize in a raffle. Those all have different odds. Okay, so let's get on to the getting started section of this book. So first thing we have is a chart. So getting started, you'll need 2 coins for this. The chart goes into fractions. That's just dividing. But we can do this. Okay, so we have 25 over 80, fraction in simplest terms, so we reduce this. They both have a common of 5. 5 goes into 25 5 times, 5 goes into 80 16 times, so we got 5 over 16. That's our lowest fraction, simplest term. Divide that, we get this as a decimal, which converts to 31%. We're going to be doing this throughout the booklet, reducing and finding the percents of things. So 6 over 60 is the same as 1 over 10, because 6 goes into 6 once, and 6 goes into 60 10 times. And that's about 0.1, which is 10%. And then 50 over 50 is same as 1 over 1. 50 goes into 50 once, 50 goes into 50 once, 1 over 1, which is the same as 1, which is the same as 100. Hint, to write a fraction in simplest terms, divide the numerator and the denominator by the same factor. Use the greatest common factor. So that's exactly what we just did. Okay, number 2. Multiply. Write each answer in simplest terms. So 1 times 2, 3 times 5, we have 2 over 15. 3 times 6, 6 times 8, we have 18 over 48, which reduces to 3 over 8. Okay, next, number 3, write each ratio. So this is black, that's gray, 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 black, 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 gray, 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 gray. Okay, a little bit easier to see now. Black to gray, the ratio for 1 black, we have how many other grays? Well, we have 3. For 1, what's the ratio of gray to black? Well, for 3 grays, we have 1 black. What about gray to all? Well, we have 3 grays, and we have 4 total. Black to all, 1 black to 4 total. When it's a bit more, black to gray, 1, 2, 3, 4, 2, 1, 2, 3, 4, 5. Gray to black, 5 to 4. Gray to all, 5 to 9. And 4 to 9 for black to all. And the dot dot is just how you write a ratio. We have 1 black for 3 grays, and we just write, that's 4 basically. Okay. Mark each probability on the line. So we have a bunch of percents right here. Where do they fit? Well, we'll break it down. 50 is about halfway, which would be right here. Then we have 25, which is half of that right there. So that one's done, that one done. 75 is about there. 95 is pretty close to the 100. 30 is a bit more than 25. And 5% is pretty close to the 0. So probability number from 0% to 100% that shows how likely it is that an event will happen. So that's what probability means. And we'll be using probability a lot in this booklet. Okay, number 5, we're dealing with ratios. Write each ratio in simplest terms. So this would be like if we had 6 black dots to 24 gray dots. Well, we can reduce it. 6 goes into 6 once. 6 goes into 24 4 times. How about this? Well, 6 doesn't go into 28. 3 goes into both of these though. So 3 goes into 6. No, it doesn't. 2 is the common. 2 goes into 6 3 times. 2 goes into 28 14 times. So that's how we reduce those. Okay, number 6. Is each statement true or false? It is likely that I will have homework tonight. True if you're watching this video. It is unlikely that I will go home on a bus. True, Mr. K bikes. There is a 100% chance that I will be at school tomorrow. False. It's never 100%. I could get hit by a bus, you never know. D, there is a 0% chance it will rain tomorrow. False, weather's pretty tricky sometimes. So hint, 100% chance means that an event is certain. A 0% chance means that an event is impossible. So, just so you know. Okay, now we have Yanni. He drew this tree diagram to show all the possible outcomes for tossing 2 coins. Coin 1, coin 2, outcome, a resultant event or experiment. Hint, H and T means that heads are tossed the first time and tails the second time. So we got heads, tails, heads, tails, heads, tails. Outcome, heads, 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 tails, tails, heads, tails, tails. So we have 1, 2, 3, 4 possible outcomes. Circle the outcome, 2 tails in Yanni's tree diagram. Okay, so 2 tails right here. Underline the outcome with 1 head and 2 tails. Right there, I guess, yeah. Next, toss 2 coins 20 times, tally your results. So for simplicity's sake, I'll just make this one up. Oops, that's 5. Okay, how many times did you get 2 heads? So we're flipping coins. 2 coins, we flip them. How many times did you get 2 heads? Well, we got it 3 times. How many times did you get 2 tails? We got it 4 times. How many times did you get 1 head and 1 tail? 5, 10, 13 times. Emily says that if you toss 2 coins, 1 head and 1 tail is more likely than 2 tails. Do you agree? Well, in our example, I would say yes. I agree with Emily. When I tossed the coins, I got one of each more often than I got two tails or two heads. Depends on your results, though. This could be different, right? Okay. That's a weird worded. Underline the outcome, one head and two tails. Weird. Okay, so that's the kind of beginning section. Now we'll move on to 10.1, experimental probability. So this usually the intro videos for chapters are a little bit longer, and that's fine. We'll continue on in 10.1. So you will need 2 standard dice, 4 counters, 2 marked and 2 unmarked, and a paper cup. We'll go over that as we come to it, and we'll see what we need. So try these, right? 12, 20 as a decimal. Well, you just divide them. 0.6 is what you get. Divide these two, and as a percent times by 100, you get 34. Cool. Next, we have Ali sells cars in Kamloops. The dealer records show that one of every 6 vehicles Ali sells is recalled for repairs. What is the probability that at least one of the next 2 cars that Ali sells will be recalled? So you can use dice to determine the experimental probability that a car will be recalled. Why is rolling 1 die a good way to model this probability? Well, it said in the question 1 in every 6 vehicles, and a die has 6 sides or 6 possible outcomes, so that's why we could use a die. The outcomes are 1, 2, 3, 4, 5, 6. The probability of rolling 1 is the same as the probability of a car being recalled. Right? So, experimental probability, the ratio of the number of observed favorable outcomes to the number of trials or repetitions in an experiment. So we're going to be using ratios, the number ... number thing. So 2 says work with a partner, roll 2 dice to represent selling 2 cars. Use rolling 1 to represent a recall. Roll 60 times and tell your results. So yours will be different than this one. You can try it, practice it, because you'll have to know how to do this. I'm going to make this up for myself just so I have some data. We'll just go 42 for this one. Okay. So our little formula right here is what we're probably going to be using for the rest of this book. P, rolling a 1, equals favorable outcomes divided by a number of trials. So our favorable outcome is rolled 1 and divided by a number of trials, which we told was 60. How many times did we get roll of a 1? Well, 5, 10, 15, 16, 17, 18. So 18 times. Results for us. 18 rolls with 1 in 60 trials. Results for 2 repairs. For 2 pairs, 39 rolls with 1 in 120 trials, because we just doubled the numbers. Result for the class, let's say 315 to 900. Awesome. Let's keep going. I'm sure it continues on to the next page. Yes. Number 3. What is the probability that at least one of the next 2 cars that Ali sells will be recalled? Write your answer as a fraction, a decimal, and a percent. So the probability is, well, it should be, we'll use the big one, 315 over 900. And we could also use 39 over 120 or your number. So let's see what 39 over 20, or 200, I mean. You can use yours, it doesn't have to be the class, but boom, boom. I get 0.35 or 35%. So reflection, do you think the results for you, 2 pairs, or the class gives the best likelihood that at least one of the next 2 cars Ali sells will be recalled? The bigger the sample, the more accurate it would be. So let's move on to the example. Sandra has her own business printing custom t-shirts to test a new screening machine. She printed 400 shirts. Trial 1, she checked 8 shirts at random. She found that 2 had errors. Trial 2, she checked 100 t-shirts at random, and she found that 4 had errors. How many errors would you expect in 1,000 shirts? Okay. Experimental probability for trial 1. We have favorable outcomes divided by number of trials equals, we're looking for errors over shirts printed. 2 over 8, because it was 2 over 8. We can reduce that to 1 over 4. Experimental probability for trial 2, errors over shirts, we did 4 over 100. This as a percent is 0.25. This as a percent is 0.04. So this is 25% and 4%. Does trial 1 or trial 2 give Sandra a better idea of the number of errors in other print runs? Explain. Well, trial 2, I would say, gives her a better idea because there's more shirts. There are more shirts. So trial 1, 25% of shirts have an error. Maybe just that batch of 8 had more errors or something, versus trial 2 had a larger sample size, so it would more reflective of 1,000, because you could just times it by 10. So instead of 4 out of 100, you'd get 40 shirts would probably get errors on it. So it's better when your sample size is bigger. How many errors would you expect in 1,000 shirts? Well, I just did that. 4% of 1,000 is 40. You just do 4% times 1,000 on your calculator and you'll get 40. So about 40 shirts will have errors. Why is a printing error a favorable outcome for Sandra's experiment? Because that's what we were looking for. Our answer necessarily isn't a favorable outcome, but she wants to know what the errors are, so that's why it's favorable. Okay, on to the practice. I'm gonna be eliminating some questions in here. Let's see, Nat conducted, so I'm gonna do 1, I think. We won't be playing this one. Slahal. And you guys can do the paper cup thing. And number 4 and number 5. Yeah. Okay, so I'll start number 1. Nat conducted experiment spinning the spinner at the left, right over here. These are his results. Record the frequency of each result. Spin 1 tallied 3. Spin 2 had 2. Spin result of 3. He got that many times, that many times, that many times. Good. How many trials for the experiment did he do? Well, let's do the frequency here. So 4 is 4. 2 is 2. 6, 4, 3, 5, 1. Good. Add that up. It's 25. He did them 25 times. So he's spinning this thing, and he got 1 4 times, then he got 2 2 times, then he got 3 6 times as he spun it. So what is the experimental probability of spinning each result? Write your answers as fractions. So for 3, he got 6 out of 25. So 6 out of 25. For a result of 6, he got 5 out of 25. An odd number. Odd numbers are 1, that one, that one, and that one. So add them up. 14 out of 25. A number less than 5 would be this, 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 and this, which adds up to 16 over 25. And then a number 2 or greater, which is everything except number 1, which would be 21 over 25. So that's it for that one. We actually don't have to do, oh, and an even number. There's 11. Even numbers because there's 14 odd. So pretty easy, not bad. Moving on to 3. So this one I will let you guys do. It's about flip cup. I know you all have access to flip cups. When you toss a paper cup, it could be paper cup, it could be plastic cup, it can land on one end or on its side. Try the experiment 50 times and tally your results. So just count how many times it lands on the side, on the open end, or on the closed end. Really try to get it flipped up, because I've gotten some cool results seeing if I can land it. And then tally them up, write them in here. What is the experimental probability that a cup will land on one end? Express your answers as a fraction. So remember, example, I'll give you the formula. P is landing maybe on one end. So that's what you're looking for. Is the favorable outcome divided by number of trials. So your number of trials is obviously going to be 50. So whichever one you're looking for, if I was this one, I got maybe 500, not 500, sorry, 5, then I'd be 5 over 50, and that would be 10%. So the experimental probability that a cup would land on its open end is 10%. What is the experimental probability that a cup will land on its side? Well, you just use your answer for this one over 50. So pretty simple stuff. I'll do number 4. Let's see, many species of birds in the Yukon nest inside trees. Researchers set up 80 boxes. Birds used 41 of them. Which is the experimental nest box will be used? Well, that's just this divided by this. So that's pretty easy for you. That divided by that is your, so you're gonna get a percent. Okay, 5. Manufacturers often test whether sample items from their production lines are defective. Manufacturers use the experimental probabilities of their test to estimate how many of all of their items are defective. How can they do this? Manufacturers determine the percent of the item with defects in their samples. They can estimate that the same percent of all their items will have these defects, just like we did with the t-shirt thing. So that's number 5. Awesome. Next video will be about 10.2. Stay tuned.